Okay, today's lab is that we're going to test this sample, actually a group of these, and there's two sets of layups on this material. There's two plies, top and bottom, which are parallel, and on this particular sample, the middle ply, the grain structure is orthogonal to the top and the bottom ply. What we're going to do is to run an experiment to see what effect the depth of this edge is, or the crack is, relative to the total strength of the beam. This particular sample would be CLT, cross-laminated timber. And so as part of this, we have to know what the sample looks like. We have to know what our test geometry is. On this one, we're going to apply a force here, essentially a force here. So we're going to set it on top of two supports, and we're going to press at the midpoint between the two ends, two load points. In order to do that, we have to find all of our test equipment. And because our lab is a general purpose lab, either the equipment will be set up after somebody has left it, or it'll be left empty, which means that you'll have to go and find all the appropriate pieces, which is about half of the testing time that you'll spend is finding and doing all of your equipment set up, getting everything calibrated, defining how your software works, how all of your data files will be labeled. So, Dr. Nairn and I, prior to starting this video, went through, we have spent approximately an hour getting everything set up before this. So now we're going to spend a little less time because we know where all the parts are, and we will again just reproduce our setup. So on this side, this frame is the universal vertical test frame. It has two lead screws inside of the columns that provide travel for this, what we call a crosshead. So this moves up and down. Inside of the crosshead is a force measuring device. We call it a load cell. And we have a couple of different sizes. So the first thing you have to do is ask yourself, what is the maximum force that your sample might produce during your test? Which means that you have to go and look up some data and make some estimates about what those numbers might be. Not only the amount of force, but how far this might deflect. Because when we're running the test, at least we have to have a rough idea of what these are to assure ourselves that the test is going reasonably. This particular load cell is rated for 100 kilonewtons at its maximum. In the bottom of this is a round hole, and into that we will put in this device, which is actually made up of a couple of, it's an assembly. So there's an adapter, this upper part, which comes off. So this end goes up inside. This piece, which we can switch out for a variety of different tools, provides the contact support. And in this particular case, the contact is a radiused contact point. Sometimes you might use something that's like about a 2 centimeter diameter dowel or a cylinder. Sometimes you may use something as small as a regular common nail to press on. But that's dependent upon your testing. We have chosen this one because it's convenient size, and it's also one of the sizes referred to within the ASTM test standards for small clear beam samples. So this assembly is all connected using some precision pins, and there's a different size pinhole between the upper and the lower sample. So at this point, this is kind of some of the hardware. This is the back support. Currently we've got this set up for approximately 80 centimeters?
400 millimeters.
400 millimeters, 40 centimeters for a span. This big black piece underneath here has these support pieces. One end pivots at 2 places. The other end, which you might not be able to see clearly, has a single pivot. It does not do this motion. You can't have all of the pieces totally flexible, otherwise your sample will just fall out of the test frame. And we had to make a choice as to, for example, which one of these ends goes under which end of the sample. So at this point, we have our load cell installed, and in order to move the frame, this system requires the control program for the frame to be operative. This particular manufacturer is called Instron, and they have a segment of Windows-based software which runs their control program. Once the control program is up and running, that allows us to move manually our crosshead. And you can hear the motor start up, and you can see the crosshead changing its vertical location. Because you have no idea where this might be after the last user, and you have to have some clearances in here in order to assemble all of your pieces. During this, I moved it up so that it's out of the way. On our display, what we see on the screen is based on a template, very, very much like a lot of other software. This system is both used in a research context, which means we have no idea how the user might use this system or what kind of testing. It's also sold and used in commercial real-time test systems for quality control testing of fasteners or whatever. Could be plastics used for embedded knee joints, for all we know. In a more dedicated system, somebody will have built a template, and then the user, usually a lower salaried employee, would come in, bring up the software, and run the same template every day for years, for all we know. So, in this particular case, Dr. Nairn and I set up this initial template. In this case, we have decided that we're going to put our force on this side in newtons, and on this display, a digital display, which is in this case, this is the default startup for the machine. So we've got newtons and newtons, and we have no idea where the machine is setting in position. So the first thing I'm going to do is go over and select out of a menu. I want to start a new sample because this is a listing of previous tests in essentially a history. Because we were last running this, I know it's the first item on the menu. And associated with the name of the template is a data file where all of the test results are going to be saved. So I'm going to select that, the name of the file. At this point, the software retrieves all of the setup information, configures the displays, downloads a bunch of control commands and code to a processor which is actually running the frame. And as part of this running, there will be some relays that click and so on. At this point, the first item in here will be what name do we wish to associate to this group of data files that we're going to produce. That's a user variable. Right now, it's called cracks_2. And the second line down here tells us what directory on the Windows system this data is going to appear. In this case, it is C, test data, labs, Nairn crack 522. So inside of this subdirectory will be a whole group of files, and those files are the control code that is being used to generate the data, so you have total documentation 2 years from now. Plus you have the rawest form of the data, which is force and deflection. Also included in this system is a group of utility tools which will allow you to post-process all of the data to produce any kind of results that you might desire. So the raw data is preserved. The intermediate data is recalculated anytime you re-enter the program. So it says cracks 2. I'm going to come over here to where it says next. And it opens up. We have made some preset definitions for a few things. For example, the name of the laboratory, the company, the test rate, which is probably the most common thing that you'll need to know. What velocity do you wish the crosshead to move during the test? For this, you either have to resort to looking at ASTM test standards, which will have specified values for those, to maybe 2, maybe 5, maybe 10 millimeters per minute. Also within the test standards, they could define it that they want the test to run something between 30 seconds and 10 minutes to failure. Then you have to ask yourself, what range of estimated forces or displacements your sample is going to take. Is it going to take 5 minutes? Is it going to take 10 minutes? And then you have to ask, how far is it going to deflect? And from that, you can calculate or estimate a velocity. So you have a variety of ways. For this laboratory, because we're impatient people, we will start off, since we don't know either how long this test is going to take, we have started it with 2 millimeters a minute. Probably after we take our first set of data here, we will say that needs to be 3 times faster, because we don't want to take 30 minutes per sample, because we have quite a few samples to test. So in a production system, you may follow code, so many millimeters a minute, or you try to run it fast enough so that you can collect good quality digitized data. That is, you're not moving so fast that the physics of the problem is too fast for the data acquisition, or because you're trying to examine the sample during real time, the sample is either going so slow that you turn your back and it breaks, or before you're even ready, it's broke. So some idea, some guesswork, optimization is required for any kind of testing. So this particular sample is going to be running 2 millimeters a minute. It's essentially in a 3-point loading system. In other words, we're 2 supports and a reaction force, in this particular case, in the center between the 2 supports, so it's definitely centered. And we've entered roughly what the beam geometry is. In this particular software, this test, really to do any further calculation, the software isn't set up for doing this particular specialized test. So we'll just do a rough set of data on this. So the next thing we're going to do, these samples are in fact about 35 millimeters in beam width, that is in this direction, and about 70 millimeters in thickness or depth. And again, there's the specimen length, and then not to be confused with this span, which is based on the geometry of the test. So I'm going to move to the next choice here, and I'm going to say Machine is ready, it's setting. At this point, we can enter a sample-specific label that goes with this. In this particular case, when I was cutting out the samples, I put 2 marks all the way across the beams when they were CLT, and I labeled them left to right on the panel as I was cutting them from 1 to 15, I think.
Or 20, maybe.
1 to 20. So we're starting with 15. This particular sample is out of the ASTM standard humidity room, which is approximately 70% relative humidity and 20 degrees C for temperature. So it's since I cut these samples maybe 2 weeks ago, with this geometry, these samples are pretty well equilibrated. Plus, the material was reasonably close to those conditions before we even glued them up. So these are pretty well conditioned, as we would say. So the next thing is I'm going to take and put my crosshead in place. Right now you can see that we have some flexural value here, flexural load. We have a funny extension that's negative. It's just an arbitrary position where this device started when we initially powered the system on. So the next thing I'm going to do is I'm going to hang my crosshead or contact point in here. This upper ring removes some of the slack out of this system so it doesn't wiggle around too much. Now I've added a reasonable amount of mass onto this load cell. And now it's setting at minus 24 newtons. I'm going to arbitrarily call that value 0. There's no force on the sample. There's no sample. We'll just call that 0. I'm not going to change or 0 the position. I'm going to do that after I put the sample in. So first thing I'm going to do is bring the sample in. I have pre-marked the pedestal with a couple of pieces of tape so that I can tell where the sample is centered in the off-axis direction on both ends, and I can see both ends. I'm going to take it, I'm going to mount it so that this is vertical. I could also use a mark here and a mark on the beam if I wanted to provide some repeatability on this. Now I'm going to manually run the crosshead down. You can see that the head is coming down closer and closer. Also, if you were to look over here, the position is changing. And what I'm doing is I'm looking at the clearance underneath here. Okay, and I have a little bit of clearance there. We've got approximately 1 Newton showing on there. It's not 0, it's 1 Newton. This load cell is 100 kilonewton, 100,000 newtons. So this represents approximately 2 parts per 100,000 of full scale. That's well within the machine's sensitivity. So I could, if I wanted to, I could rebalance the load at this point. I could arbitrarily call it 0. It may drift around a little bit. This tells us something about the accuracy and precisions that we might want to limit our reporting of our data to. So at this point, since I've seen it have approximately 2 newtons of difference between 0 values, I'm probably going to say this data is good, plus and minus 2 newtons. I don't know any better than that at this point. But you notice that we've got many decimal points up here. Those are noise. And those of you that have grown up in a fully digital world are used to looking at those digits and thinking that they're real. They're not real. Not as far as the data is concerned. That's all noise. So if I were to slowly bring the crosshead down, and what I'm doing is that I'm looking at the load. Oh, now the load started to go up. Now I've got 10 newtons on it. I'm going to go lower, so that is the contact point. I'm going to move up slightly, and I'm going to reset the zero displacement value at that number, whatever it is. There are slight variations in the sample thickness that will change as we do our testing. So again, here we are at about zero force, zero deflection. These are millimeters. So got a lot of decimal places. That isn't very much displacement. So now what we're going to do is we've got 2 millimeters. Now I have to define what our sample naming convention. So I'm going to call this one, I'm going to put the letter C, it's, let me get rid of the cat, okay. C for cross-laminated timber. The sample number, which is 1,5. I'm then going to go an underscore, and because of the way that we've designed this experiment, we have four essentially cut out thicknesses. A half of a ply, 1 ply, 1.5 plies, and 2 plies. And so for our naming convention, I'm going to call that one 0.5, or 1/2 of a ply. That way we can look at our data file names and we have a direct association for what the samples are. So now, I think we're ready. When this starts, the screen is going to change and it will show us a pre-programmed graphical display of force and displacement. Last chance before we break our sample incorrectly. So in this particular display, the display dynamically rescales. So now we've got approximately 1 millimeter, 0.8, 0.9, 1 millimeter of deflection, and we're up to nearly 1,000 newtons.
Maybe I'll zoom in.
Now we have to, what we expect is a crack development over in this area, down in here. There's 2 ways we can tell that. One of them is when the crack develops, it releases a lot of energy, which makes noise. So we're fortunate that we don't have a class of 30 students in here all talking, because I can actually hear it cracking. I should be able to hear it cracking. It is not cracked yet. The other thing is that when it does crack, there will be a decrease in the force for a short period of time. So we're just sitting here waiting. So we're up to 5,000, 6,000 newtons. So this is the point in a lab class I will turn to the students and say, what do you think the force is going to be? If it were a clear piece of wood out of well, this is actually southern yellow pine, with this geometry, what would it fail at? Oh, I'm hearing it. And we can't tell. It could be, all I can see is the outside of one face. I can't look at the other side at the same time, but I can sure hear it doing something. So it could be delaminating, It could be cracking in the CLT vertically. It could be cracking in the middle of the beam, and the crack hasn't gotten big enough that we can actually see it on the outside. Now, that was loud. I should be able to see something. Can't see anything yet. Up, 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 crack, diagonal, 45 degrees, right orthogonal to the growth rings in the CLT ply. Now I'm going to stop. Okay. So this is going to continue. We have not taken the displacement off of this, so it will continue to crack. We have to remember from a safety standpoint, if I put my hand underneath this and it instantaneously failed, would it hit my knuckles? So resist putting your fingers and toes where things can fail. This, because the sample size is what it is and the geometry, is relatively safe. But we test beams which are, this beam instead of being 70 millimeters is 700 millimeters, and maybe a half a meter the other direction, and maybe 30 meters long. And that has a huge amount of stored energy in it, but it's the same test. So here we've got a nice crack. It's through the wood in a radial longitudinal direction. So the tree is in this direction, which is longitudinal. And so hopefully by this time in your class, you should be able to write on the board what the strengths are for failure across whatever the surface is, whatever that stress might be, longitudinally, radially, and tangentially. And then when we look at this, the maximum load on this, just roughly, is about 8,700 newtons. And the next question is, if you had made estimates of this in class, does 8,700 newtons make any sense? Have we done the right test? Because I sure don't want to do this test wrong another roughly 40 times. I don't want to spend another 2 weeks making samples and waiting for them to acclimatize. So there, in this particular case, we have lots of replicate samples. In our laboratory, we do at times testing where we only have one sample. You only get one chance at doing your tests. And so to say that at times the anxiety levels are a little high, and when you make a mistake, it's always expensive. So the emphasis on knowing what you expect is really important. So this sample, which is labeled 13, is the Glulam layup. All three plies parallel. The question is where would you expect this to break? So this is going to break in the middle of this ply, in the center ply, like the other sample did.
What do I expect it?
No, I don't. You should know. This is a question to the viewer. As you're sitting here waiting. So the last sample went up to about 7,500 newtons. We're about halfway to that force now. And at this load, before, we could hear it cracking. It's been completely quiet. So we have passed through 9,000 newtons, 20% more than the first sample. No noise. There are no small deflections and force noted on the graph. Oh, and we have a display error up here that says overflow. Fluctual load newtons and switch it to kilonewtons and done. We had too many decimal places to display. There was nothing wrong with the test. It's just a setup in the menu on the template file. Oh, I'm hearing it. Notice the shape or the nonlinear shape of the force deflection curve. And the first question that you ask yourself is, what causes that? Bigger crack. So we're close to twice the force level on this sample. So if you were the engineer and you're, or worse yet, the insurance underwriter for the engineer.
I see a crack, I think.
So we are starting to see a little crack right here at the notch. And it's very slowly starting to propagate horizontally in this material. Oh, it's out here now, the crack.
I think we can stop it.
Okay.